Okay, so we postulate commutation relation. So for these, we postulate commutation relation. And what are those both for bosons and fermions? So the commutation relation psi sigma prime of R prime psi sigma double prime of R double prime minus minus is for fermions and sorry, minus is for bosons and plus for fermions. And then we have sigma R sigma double prime of R double prime and sigma of prime and R prime, which is equals to 0. Similarly, we have for dagger sigma prime of R prime with a dagger and sigma double prime of R double prime with a dagger, and we have a minus plus uh, sigma double prime of R double prime with a dagger and sigma R prime dagger of R prime equals to 0. And finally, uh, between creation and annihilation, sigma prime R prime sigma double prime R double prime with a dagger minus plus sigma psi double prime with a dagger R double prime and psi sigma R prime equals to Kronecker delta function R prime minus R double prime and sigma prime and sigma double prime. Yeah. So these are basically the commutation relations which we have postulated, where where uh, minus refers to bosons and plus refers to fermions. Yeah. They will, and then as before, we can write also a number operator. To give the total number of number of particles, और वो कैसे आएंगे? That would be n. This is sum over sigma prime integral d3 r prime psi sigma prime r prime with a dagger and psi of r prime. Yeah, और ये sigma prime. And what does it measure? And in some sense sigma prime dagger r prime and sorry sigma prime r prime uh, measures the density of particles, the density of particles of a spin of spin sigma prime at location r prime. Yeah, similarly, you can also write it for n double prime as well. Yeah, so this basically measure the number of particles. So, in fact, that corresponds to the density of particles having certain spin sigma prime at a certain location. So, energy terms that would appear in Hamiltonian वो भी लिखी जा सकती हैं using these operators in a same manner or in a similar manner as we did for A dagger and A operators. Uh, so energy terms appearing in Hamiltonian can also be written uh, for the field operators, for the field operators in a similar way as done for A dagger and A. So then you remember an additive, अभी पीछे हमने additive one particle quantity जो हमने ड्राइव की थी, that was K uh, becomes in general कैसी हो जाएगी this property K would becomes for sigma prime, sigma double prime, integral d3 r prime, integral d3 r double prime, uh, psi sigma prime of r prime dagger. Then we have r prime sigma prime sigma prime and K double prime and sigma double prime. Then we have this psi sigma double prime r double prime or let's contradict it. So we have this, and for two particles and two particle interaction term क्या हो जाएगी? ये हमने एनर्जी निकाली थी और टू पार्टिकल इंटरेक्शन टर्म would be equals to half integral d3r1 d3r2 d3r3 and d3r4. Then we have sigma 1 r1 dagger, then sigma 2 r2 dagger, Then we have the matrix elements of R1, sigma 1, R2, sigma 2, and the V, then R3, sigma 3, and R4, sigma 4. So rather than using prime and double prime, we are using 1, 2, 3, 4 for two particle system, sigma 3, R3, and sigma 4, R4. Yeah, so this is basically your, in fact, interaction energy. Yeah. Uh, in fact, we are basically representing some sort of coordinate space representation. But what we need to know are those matrix elements. So, in fact, this is the important term which we need to know. So, this is the matrix elements. That is what is counted here. Now there are certain notations on multi-particle state vector, वो भी लिख लेते हैं, then फिर बस एक आर्टिकल रह जाएगा आपका इस उसका. So let's talk about some notations. Notations of multi-particle state vectors. Yeah. So remember हमने one particle or a single particle state by creating one particle from the vacuum, वो हमने लिखी थी जिसको हमने psi I कहा था. Yeah. So अब हम multi particle कर रहे हैं तो we need to write a notation for psi n. So uh, a single particle state for a creation operator that was represented as uh, psi I, और उसको हम लिख सकते हैं 1 because we have just single particle, और इसको हमने शुरू में कहा था if you remember ki. या और ये किसके बराबर था? This was in fact ai dagger ground state. ठीक है. So further applications, जो further application of other a dagger, that is creation operators, will add more particles. Yeah, will add particles to the same state uh, with with either with either bosonic or fermionic symmetry. Yeah, bosonic or fermionic symmetry, दोनों के लिए. ठीक है. And then the multi-particle state क्या हो जाएगी? That would be represented by psi superscript में n, psi n. And so सिंगल पार्टिकल स्टेट हमने डिफाइन किया, उसके अंदर हम मजीद क्रिएशन ऑपरेटर ऑपरेट करवाएंगे, तो दैट वुड गिव यू अ टू पार्टिकल स्टेट दैट वुड बी रिप्रेजेंटेड एज साई ब्रैकेट में 2 फॉर 3 फॉर 4 एंड सो ऑन फॉर n. So that is you know this goes on, so one could think about as, so this is 1, then one could write 2, then one could write 3, and so on up till psi n. Yeah. So a Khas state is one where two particles is at position r1 with spin sigma 1, and uh, and this is some special case, and this special case would be for a for a boson, let's say. So a particular special case is one where two particles is at position r1 with spin sigma 1. Uh, one can one can use the field operator on the vacuum. And what is that? क्या हो जाएगा? So we have a state where two particles are at the same position r1 and having the spin sigma 1. This would be psi operator sigma 1 r1 with a dagger here operating on vacuum, or r1 sigma 1, oops, r1 sigma 1, this is equals to vacuum, its complex conjugate sigma 1 r1. Yeah, so without dagger. Uh, we can use these terminologies, uh, uh, terminologies to sort of recover the usual one particle wave function from the Schrodinger equation. Yeah, so those wave function, those terminologies can be used. So then one can use these these things to recover the usual one particle wave functions for the associated Schrodinger equation. And so one could use those wave function as psi of r1 comma sigma 1 not comma, which is equals to uh, r1 sigma 1 or psi 1 psi I, which is equals to sigma 1 r1 or psi I of 1. Yeah. And you can generalize this to n particle state. To n particle state, and its associated coordinates कोऑर्डिनेट स्पेस वेव फंक्शन वो क्या हो जाएगा? दैट वुड बी साई ऑफ R1 sigma 1 comma R2 sigma 2 comma so on Rn sigma n is equals to 1 upon the normalization factor, correct normalization, n factorial 0, the ground state, starting from the ground state, psi sigma 1 R1, psi sigma 2 R2, so on up till psi sigma n Rn of psi n, bracket close. So these functions, you know, क्योंकि we are talking about symmetric and antisymmetric or bosons or fermions. So these functions are either symmetric, that is for boson, or antisymmetric for boson, under interchanges of any pair of these Ri's and sigma i's with Rj or sigma j's. Yeah. So this function is either symmetric, any for bosons, and antisymmetric for fermions under changes of any pair Ri sigma I with Rj sigma j. Yeah. और ऑब्वियसली इसका इनवर्स भी निकाल सकते हैं, यानी वी आर बेसिकली finding the value of this. We can also find the inverse as well, और जो कि बुनियादी तौर पर psi n होगा. The formula has also an inverse, and what is that? Psi n, which is equals to 1 upon root n factorial sigma 1 sigma 2 so on up to sigma n integral dr1 d3r2 so on up till d3rn, and you would have psi sigma 1 dagger of r1 acting on vacuum, and times psi of r1 sigma 1 so on up till rn sigma n. This is the inverse of the above formula. So these two expressions are something जो कि बुनियादी तौर पर एक दूसरे का Fourier transform है. So we can call them as Fourier transform pairs. So the two expressions are something called as Fourier transform pairs. Yes, Fourier transform pair rather. और जो factor है n factorial, it is basically the normalization factor, and the correct normalization जो है that would be equals to 1. So the vector n factorial in root needed so that the normalization is given by the normalization is shown up to sigma n integral d3r1 d3r2 so on up till d3rn, and we have a mod of psi of r1 sigma 1 r2 sigma 2 so on up till rn sigma n with a vector sign here whole square, and this has to be equals to 1 for the correct normalization. और इसको हम क्या कहेंगे, where this quantity psi of r1 sigma 1 r2 sigma 2 so on up till rn sigma n whole square can be viewed as a multi-particle probability density. Distribution. Yeah. So this is basically some notation. So we are successfully in the domain of multi-particle dynamics or many particle systems, जो कि बुनियादी तौर पर हमने इससे start किया था. Now we have a last article which is basically multi-particle dynamics, because once you have developed everything, the operator, starting with the physical variables or the dynamic variables, promoting them to operators, then developing their constraint relations, that is commutation and anti-commutation relations, and then finally you started for the single particle dynamics, now for the multi-particle dynamics. So uh, we would do some sort of a state notation in Heisenberg picture, और Heisenberg picture के अंदर state notations In जो है, that would be the number of particles in n1 state, number of particles in n1 state, number of particles in n2 state, number of particles in n3, and so on, number of particles in n state. And then these number of particles are basically generated by applying the operators AI dagger, so multiple times. Yeah, we can then suppose the Hamiltonian from these journal terms. So let's start the description. Multi-particle dynamics. So we have some discrete state notations, or वो discrete state notations in Heisenberg picture, and notations in Heisenberg picture. And what are those? So we say that psi n state can be represented as n1, n2, n3, so on up till nn, in fact. So this is a discrete state notation or representation, uh, and these are generated, generated from generated from applying a dagger, AI dagger operator, yeah, or rather operators. Yeah. Now we can suppose the Hamiltonian from the journal terms. Yeah. Now let's say we suppose the Hamiltonian from some journal terms from journal terms. And what is that? So let's say इसको मैं इस तरह से लिखूं Hamiltonian को, and this would be summation over k comma l, a k dagger of this k h naught l a l plus half summation over q r s t. एंड रिमेंबर जो हम इससे पहले कर चुके हैं, सो काइनेटिक एनर्जी एंड पोटेंशियल एनर्जी टर्म्स. सो ए क्यू dagger, a r dagger, q r of this v t s times as and at. So we have this due to addition of one particles and two particles interaction. So this is due to additive one particle and two particle interactions and two particle interactions. Yeah. So Heisenberg picture के अंदर we find equations of motion, जो कि बुनियादी तौर हाइजेनबर्ग पिक्चर में बुनियादी तौर पर जो ऑपरेटर्स हैं दे आर फंक्शन ऑफ टाइम, whereas the state vectors are not function of time. So जो उनका algebra है that would be somewhat different, and वो algebra हम यहाँ पर निकालना चाहते हैं, and we would write the Heisenberg equation of motion. So in Heisenberg picture, uh, equation of motion, equation of motion for AJ dagger which is a function of time. Yeah. So remember, operators are function of time, and gives some algebra valid, which is valid for bosons and fermions. fermions. And that algebra जो है वो क्या हो जाएगा? So we have AJ dagger, sorry, AJ AJ comma AK dagger AL. This is equals to AL delta JK. Remember ये हम पहले लिख चुके हैं. And this can be written for AJ comma AQ dagger AR dagger AS AS and AT, and this is equals to uh, sort of this is equals to AR dagger AS AT delta JQ plus AQ dagger ATAS delta JR. Okay. So or now we can write the equation of motion, the Heisenberg equation of motion. So then one can write equation of motion for bosons or fermions. And what is that? Iota h bar d aj upon dt, which is equals to aj, the Hamiltonian, which is equal to summation over L J H naught L A L plus summation over Q R and S and S. So A Q dagger A R A S times JQ V and SR. Yeah. And remember यहाँ पर हम जो बात कर रहे हैं, here we are saying that all these in fact A's, that is all these operators, annihilation operators, they are evaluated at time t. So since we are using the Heisenberg sort of algebra where the operators are function of time, so where all A's all A's are evaluated at time t. तो, यहाँ पर एक चीज जो आपको देखनी चाहिए वो नॉन लीनियर इक्वेशन है, and this non-linearity is due to interaction. So this is in contrast to our usual basic Schrödinger equation जहाँ पर non-linearity नजर नहीं आती. यहाँ पर non-linearity जो नजर आ रही है, this is basically due to interaction. So it is noted that